Thanks to Shita Broda for inviting me here for this conference school. I didn't actually have much idea of the crowd prior to I came over here. While going through some of the previous talks, I got a bit of an idea. I changed my slides there for a bit. I diluted parts of it because this is too empirical in that sense. Okay, so if you are because of the shortness of time, 1 hour isn't enough for all these concepts which I'm going to talk. So if you find something, just try to check online or ask me after the talk so that I can just kind of explain. So how many of you, just to get an idea, so all of you I heard are from UG, right? From undergrads? All the students? Some are PhD students, okay. And how many are from physics, maths, biology? Okay, so fair amount. This talk, this is the first time I am going to give this talk, so it will be great to have some feedback about this. So, and it actually deals with the network of debating parliamentarians in the upper house of India. So prior to the lunch, you had the data on Japan. Now it's time to look into the Indian data, right? Because India has too much of data. Point is you have to look for it, and then you have to do some analysis on that. So this idea came up probably 6 months back, I think. And then I scraped the data from the site. I will show the link, and then I started to do the analysis. There are a bunch of ideas which are currently I am doing on my own, because the no students, it's hard to get PhD students in a business school and who will be interested in this kind of work. So I'm doing it on my own. So let's have a kind of a quiz. Let's check. Can you guys just guess who made this statement? It's very easy to guess. I am certainly not enamored of, and I do not swear by, two houses of legislature.
Not Nehru.
No, you are close enough. It's quite easy. Well, sorry to disappoint you. So this is in 1931 when he made this statement in I think the roundtable conference over there. It's a long lecture if you read, but this statement is basically the thing which I wanted to show, because actually over time post independence we didn't follow this. We ended up with the bicameral kind of a system where you have the lower house and the upper house. Now in my work, what I focused on is the upper house, on Rajya Sabha. Why? Because the data is there. For the Lok Sabha, it is just I think few months back that it has been kind of cleanly made available. So I have basically started to get the data from there, but this is the data which has been there for a long time. Okay. So now, so this is the site you can check. So if you have any parallel ideas, you can get the data from here. You basically you have to know a bit of coding in Python and scraping from the web from HTML files, and then it's fairly like an easy job. I mean, except that it takes a bit of a time to get this data soon.
And this from the 1950s?
Yes, from 1952. Exactly till 2018 I had got the data. 2021 I had got the data till 2021. So the Rajya Sabha. So my focus currently is on this one on the Rajya Sabha debates. So they have been drafting rules, then procedures, then conventions and precedents. One of the key things, if you look into the Indian Parliament, is the question hour, right? So here the question hour is basically like you have the members who are going to debate with one another. So therefore you can form a link in between two participants who are coming to debate. So let's see how this you can picturize. So it's pretty much like a bipartite graph. So suppose you have a ministry, you have the title of the debate, and these are the members who are going to participate in that. So what you can do over here is that you can connect the members, like two members gets linked if they participate in a debate. So it's pretty much a bipartite graph. I think in your school, I think you might have been taught in this program, right, what a bipartite graph is. You have two partitions. So just like you have the papers and the authors, it's like you have the title and the members. So that's the way it works over here. So let's take some data from the real statements. So this is a debate on the divisional office of the railways on May 27, 1952, in between these two parliamentarians, Roth and Bishwas Roy. So you can form a link in between the two members like this. There was on the same day, we had a debate on raw silk industry, and which like involved 5 members over here, as you can see. So eventually what you will get is basically all the 5 are linked. So you have 5 nodes with 10 links. Okay. So and this way you can do it for all the debates on a particular year, or let's say 5 years gap or a 10 years gap, which I have done in this case, and then you can count the number of times, how many times this edge say exist. So Valiullah with Reddy. Okay, so it can be 10, 20, 100 and so on. So eventually what you will end up with is a undirected and a weighted graph of members of the Rajya Sabha, correct? So that's what you bipartite was basically in here, like you have the title and you have the members. So I'm connecting it, two members get linked if they are part of the same debate title. So it's just like the author and the papers. That's what it is.
So the sequence in which they speak here,
sequence, the only way to get into the sequence is into the PDF files, which is actually like a huge
what I meant, the network doesn't contain any information about the
sequence. Yes, yes. So in that case, I could have done a directed graph, which would have been like more enriching. But here, they basically the HTML files, the way it is there, like if you go to the site, you have the debate title, and then you have the members, the participated, and then you see like you click on view, then it opens a huge PDF file which is scanned. So it is very difficult to get that data. So at this point, I have focused primarily on the undirected part. So
how is the way
by the frequency of times the two members they have participated. So suppose you have another debate. So let's say Valiullah and Reddy they participated. So the link becomes then weight is 2.
Okay, so for every year you have
yes. Yeah, I have networks. So it basically for every decade, so that I can have a sufficient data for the analysis. So now, so once we have the network done, what I try to get is there are two kind of attributes which I can check, the network attributes. So the K-core index, the Bird's constraint, and the clustering coefficient of every node. So I think like everybody knows the clustering coefficient, it's basically how the neighbors are linked with each other for every node. Bird's constraint, I don't think most of you may not have heard about it. So that's fine. K-core, I think you might have, I'm not sure, right? But we'll show in a picture. So these are the components which are coming from the network, right? Then based on the exploratory the work or the analysis which I have done, I focus into two things. One is on the gender and the other is on the education. Okay. Now how do I identify the gender of a parliamentarian? It's very easy for Indian data, because for the male we have Shri, for female we have Srimati or Kumari, which isn't the case for the European data or Chinese data, where they have those algorithms to see what the gender is. For in this case, it was extremely easy to tag with the gender. Okay. So I don't actually have at this point any unknown gender or a gender which is not tagged. So this data is complete in that sense. Compared to if you see studies on such things, on gender on any other countries, you will have these issues, especially the European countries or the Asian countries and so on. Then comes the education. So what I did over here, this was the hardest part, because I had to go to the biographical handbook, which is like a 1 GB PDF file. I had to type the name one by one and get the highest qualification of that guy. So based on what I found out from the PDF book, there are 11 categories which can be given to each of the parliamentarians. Doctorate means PhD, then like UG, graduate, then professional graduate, which means like you have say you have done BSc and then you do say LLB. So that's called the professional graduate. Similarly for postgrad, then intermediate, which I think is class 10, right, or 12, and then matriculation. Under matric is basically if you are passed till 8th or 5th. So that data I basically clubbed together because there are not too many. So it is under matric, diploma, and no formal degree. So this one, no formal degree, meaning that there is no information. Okay, so I'm not saying anything else over there. So
what is the difference between graduate and
postgraduate is like say MSc. Graduate is basically BSc.
that will be undergraduate?
No, graduate, I think there is a particular thing which is there. Wait a sec. Graduate is a this thing that it is just mentioned that it is a graduate, something like that. It is there. But let me just go to the tables, because I think at some point because the number was too less, so it might be tagged with the UG. The good to point this yeah. So here I am just explaining the K core decomposition. I guess like some of you might know, some of you may not, but that's fine. So suppose you have a network like this. So in the K core decomposition, what do? You basically start with the degree of the node with degree 1, and you start to prune them. So slowly, if you go on doing it, then you take all the nodes with degree 1 and put it in a shell. So that's the K core index 1. And if you keep on doing it till you get finally the one with the maximum K core index. So here in this picture, if you see, some nodes which might have a high degree might have a very low K core index, because they are in the periphery of the network. This node has a lower degree of 3, but the K core index is very high because it's in the core of the network. So I take the K core decomposition and I find the K core indices of all the participants of the parliamentary debates, right. The second thing which I had mentioned was the Bird's constraint. So this, I think, is something which you are going to know is a new thing for you, because it's used mostly in social science. Okay. So the idea over here, take a look at this picture. I hope the resolution is clear to all. So if you look into figure A and figure B, take a look at the green nodes. So now you see the green nodes over here, they are actually acting as some bridges in between these components. They are not linked with each other, correct? So these nodes are sometimes called the brokers, because they have knowledge from diverse set of people from different modules. These empty spaces which you see over here, it's kind of imaginary in that sense, are called the structural holes. And the way to quantify the number of structural holes is basically using the Bird's the constraint measure, which I am showing over here, which essentially quantifies the direct and the indirect contact for the nodes. Okay. So check this node over here, green one, the same node is over here. Now this guy is connected to all these people, this fellow is not connected to all these people. So the structural holes over here are more, the structural holes over here are less, fine. So therefore, and this equation, I mean, like essentially quantifies the direct and the indirect contacts of these guys. So basically what it means, the higher values of this constraint for a debater imply that it's the external alters are more connected, thereby indicating fewer structural holes. So the constraint over here is more, like over here is more, because the structural holes are less. The constraint here is less because the structural holes are more. So this is like a established work in social science. So I recommend all of you to look for, like, if you type online Bird's constraint and then 1997 2004, you will find a huge literature on this work and how it has been like applied in social networks. Okay, so that's what I am putting up over here.
What exactly does the constraint quantify?
Like how constrained you are in the network. So let's say here in this case the number of structural holes are high, right, because there is no links over here. So the structural holes is sort of a like imaginary yeah, okay, it's sort of a like imaginary kind of a thing, but it's basically the links. So here you have dropped this one.
Oops.
Someone's, yeah. So therefore you see it is basically the constraint is less because it can have the information from this group and this group, right. So if this person it has to connect with this, it has to actually has to go through this guy, right. In this case the number of structural holes are less, but it is constraint will be higher.
Is equal to the number of cut sides, which is the number of links per piece.
Yes, yes, exactly. So therefore this idea is basically, this guy is a broker, we call it brokerage, which is impacting the performance. So these are the works which have been done so far, and I am using these concepts from social science into this work. Okay. Betweenness centrality will give you the shortest path, but it won't give you the indirect connections. It is basically giving you the shortest path divided by the total number of paths which is going through it. So they are correlated, but they are not the same. That's it.
So explain the mathematical definition.
Yeah. So here, this is the time you can like at this point you can, I put up the time because I have done it time wise, but at this point you can ignore that. So this is the constraint of the debater I summing over all the j's, right. So here Sij is basically the proportional measure of links between debater I on the direct contact j during the period, some time period, and Siq Sqj is the product of the proportion of indirect ties between debater I to q and q to j. So that's the indirect ties. So this will take into account the indirect ties also. So that's the part over here. So now just to give you an idea, like the kind of work I do, it's specifically very data driven, which is like first you explore the data and then you kind of ask some interesting questions and find the significance of those hypotheses. So let's take a look at how the data looks like, what are the insights one can get from here. And like as I said, the non-network attributes which I had chosen was gender and the education. So here I am doing it through time, the stacked bar charts. So here you can, like, I mean essentially do it like this in this education wise, and so here this will be the top part. So I start from the 60s because the one in the 50s is too less. So I have excluded from here, although in the networks I have put that up. So if you see over here, and this is the place where you see the under representation of female parliamentarians in the upper house. So you can see that very clearly through time. Only in the 1970s you see a slight jump. Okay. So that's probably due to the political purposes and all that. There might have been a big jump, but then again it started to come back. So it started with around 7%, and then it is right now it is stuck around, I think, 12.1%. So that's the underrepresentation in gender which we see in the data. After that, I am doing it through the decades in terms of the education. So what we see over here is that the doctorates, there are quite a few doctorates in this this data. No formal degree shows a bit high in the 1960s, but over time, as you can see, it has tapered down a lot. Okay. Then what else? Graduates also is fairly like doing well over here. PhDs also. Yeah. So the no formal degree, as expected, it is actually shrinking down.
The total number going down in the later years?
The total number has gone down because the number of debates in this decade has dropped. I don't want to say more. Kindly ask me things which I don't. So, let's take a.
So that is interesting one, that is this reflective of the constitution of the Rajeshwara members or the people who actually engage in debates? I mean, there might be, like highly educated people who don't speak a single word throughout the entire thing.
That I will show when I do the argument parts. That's the part where I'm
similarly for the women members, I mean, it could be, of course, as you say, because over women Rajya Sabha members, but it also could be that for some reason women are less likely to take part in a debate than men.
Yes, that's the questions which I will answer through the following slides, the upcoming slides. But one part is that if you check the data on its own, the underrepresentation is there since the 1950s. So in my data, it is coming around 12.1% because of the nodes network. But if you like overall, if you see, it is around 12.6% or something.
Total absolute number
Yes,
of female.
is less, comparatively less.
How about the
However,
fraction?
Huh?
How about the fraction?
That's what I'm saying, the 12%.
No, fraction of the total women content. So by normalizing by the number of female.
So,
I mean, if you normalize
network versus non-network, you mean?
the total number of female, how many fraction of the women take part in the debate?
That I think almost see, like what I
How
kind
about
of.
the male? Like how many fraction of the male takes part?
No, that is more than the 95% because in a debate, very rarely you will find one guy just going to say anything. At least you need two people to debate, na? Right. So the number of nodes which you have over here is basically exactly what is there in the network. So it is close to 95 or 98% of the data in both cases. Okay, yeah.
Would this also contain honorary doctorates?
I don't know about that. Then that has to be basically, I think, checked going to the site because I checked it through the PDF. PDF said PhD. It doesn't say like honorary or anything like that. But the
after serving in parliament, right? I mean, why would they get it? Like, so many people are
nominated. So
eminent people can.
So that categorization, I think, is a bit hard also. Like then one has to manually go and check. So interesting point, no doubt about that. But the interesting part, which I kind of try to study because I am more into the networks part, is like if I take the highest K-core index and then if I plot it. So the interesting part over here is that even though females are underrepresented, but 40% of the females, they are part of the highest K-core index. That's an interesting observation which I see over here. There was a peak in the 1980s over here. There's a slight dip in the 70s, slight up in the 80s, and over here it has gone up a bit. So the number of female parliamentarians are less compared to men, but if you check into the core of the network, the percentage of female who are part of that is quite high. So that's an interesting observation which is like existing. Interesting part over here, the other thing is that the graduates, I think the graduates over here is basically the UGs. So this blue bar will be basically merged with this because this is very few. Here you see they are increasing, same as in the PhDs. It's quite like rising up a bit in terms of the highest K-core index. So now let's see the next part, which is the descriptives of the network through different decades. And here the interesting part shows up. One is the average degree. If you see, it was quite low in the which makes sense, right? Because then the parliamentarians were few. Over the time it grows up. Then in the decades to continue, it rose up to 139.38. That's the one till the last decade so far. The network diameter, which is basically the longest of the paths which you take, right, that is fixed at 4. So, it is not going beyond that or falling beyond, it is just fixed at 4 for all the networks which is there in the study. If I take a look at the density, the interesting thing is that it seems to show me a U-shaped curve. So, first here you see it is 0.2, it falls down, then slowly it rises up to 0.28 in this decade, the last decade. So, it is basically meaning what? This network density, you know, it is the number of edges by the expected number of links. So, it is like this, it is falling and then it is going up, which means the old parliamentarians are going to leave and the new ones are coming in. That is what it possibly shows. The clustering coefficient is more or less around 0.78 or 0.8 around this thing throughout all the decades. The Bird's constraint over here is significantly low. It is around 0.063, 0.064, 0.073 and so on, which means the structural holes are quite high. Okay, so, the structural holes are quite high in the network. And these are the number of edges, and this is where I think you were asking about the last decade, that there is a drop, is because the number of the parliamentarians are less, because the number of debates were less in that decade, in the 2010 to 2021. So, now that is the like how we kind of explore the data, and based on what your questions which you actually asked through the bar charts over here, we kind of but let us take a look before that on the networks how it looks. So, it is using Gephi. I think you might have learned it in the school, right? The visualization of networks, yes or no? No, yes, okay. So, using Gephi you can draw the networks to make a cool plot in your paper. So, the color coding is as per the clustering coefficient and the size is as per the Bird's constraint. So, this is in the 80s, 90s, more or less you see at least like visually the structures are similar. So, there seems to be some three clusters which are there over there and the bunch of people scattered in the periphery. Similar things you can see in the 2000, 2009 and 2010. Yeah.
You should say the density goes down.
Yeah.
Then it goes up. Right? But the Bird's constraint doesn't follow that trend.
Yes.
So
because the structural holes, so even if new parliamentarians are coming, they are not getting into they are going into some clusters. So, they are not forming links across the clusters. So the bus constraint, if you go into the picture, it's like the green node. If the bus constraint would have gone up if you go and connected with the green node, but they are not doing it. They are going to connect with something over here within the modules, and there is no across modules which is going on. So that's the, I think, the reason why it is not changing. Okay. So what can be the research questions which I can ask based on the observations? So first thing which I try to like understand is to empirically examine the significance of the node level, I mean attributes, and the role of homophily in predicting the type formation in this data. So homophily means, I mean essentially nodes of two types will get linked compared to chance. So let's say you are A grader, so you will be friends with each other more than the non-A graders, or students in the same section will be friends with each other more than the across the section. So like that's the idea of homophily. So here what I try to ask over here, the existence of two kinds of homophily in predicting the network links. One is on the gender, the other is on the education. So are people with the same gender more likely to debate, and are members with the same education level more likely to debate? So that's the question I am going to ask through these time slices. So now to understand this, I make use of this model called valued argum. So this is, I think, a very new thing even for like people like us who are doing this kind of work, because like usually the social network guys, we focus on the argum part, which is for the unweighted network. So the network is not weighted. So it's either the adjacency matrix is basically 0 or 1. So the overall idea of how like argum works is basically what essentially it tries to find out is what are the factors which are significantly explaining the link formation. So it can, so you know, like in networks can grow in different ways. You have the preferential attachment, you have homophily, like you form links with people of the same types, you have the triadic closure, and you can form links. So here you can have a bunch of things like stored in this something called the network statistics. So ZK, okay, and these are the coefficients which we want to study, and we want to see the effect size and the significance of these coefficients theta k. Now since it is valued in the sense it's a count, because the weights of the links, so we cannot use the usual argum models. So we use the modified one, which is called the valued argum models. Now the valued argum, the trouble with that is that it's a count data, right, because it's 1, 2, 3, 4 like this. So traditionally when you are going to deal with count data, statisticians usually follow the Poisson distribution, because it says the discrete, right. However, in this case, because you cannot have a Poisson distribution, because there will be over dispersion in the data. You know that for a Poisson distribution, the variance and the mean have to be the same. But if the variance is very high, then what do you do? So there is a modified distribution which is called the Poisson distribution, the Conway-Maxwell-Poisson. So this Poisson distribution, it was first brought up in 1961 by these two guys in, I think it was a paper on industrial engineering. Okay. Then in 2015, I think Shmueli and her team who were studying some kind of sales data or something in a business school context, they tried to understand that what if the lambda is also like varying. So that's when they like independently developed this, and they found out that the Poisson has already been like established in 1961. So now what happens is that valued argum, those who like theorize this, they have given that if the Poisson distribution is not going to be your reference distribution, then you should choose the Poisson distribution. So, I have basically this H y is will be the reference distribution which you have to choose. So, these are the terms which was the z k which I showed, the z k over here. So, these are the terms which I basically showed. So, here you have something called the non-zero and sum. So, I will come to it what exactly it is. As I mentioned in my slides, I was interested in the k core index, the Burt's constraint, the local clustering coefficient, then gender, which is the node factor gender, meaning whether it is a male or a female. Node match is the homophily term, which basically means whether two nodes of the same kind are going to form a link or not. Then node factor on the highest degree, by highest degree I mean the educational qualifications, okay? And then node match with highest degree, which is the homophily term. So, that is my equation which I want to kind of like evaluate right now. So, over here let us take a look through the time scales, through the decades, what is going on. Like if I want to study this, what is going on. So, here please note these things down also. So, right now I will look into the estimates of the valued ergum and how I am going to check the model fit. So, that is through the Bayesian information criterion, BIC. Okay. So, I am going to use this word a lot, and that is what it means over here. So, it is a long thing. So, I cannot explain much, but I mean like essentially BIC is used in statistical models to compare how good one model is with another. Okay. So, if a drop of BIC more than 10, then it is significantly better than the other one. That is what the traditional rule is. Okay. And these are the levels of significance. I do not think you have yet checked on these symbols, but we will see eventually what it means. So, let us take a look at the first model for 1950 to 1959. So, this is my basic model just with the networks. So, non-zero, sum, k core index, Burt's constraint and LCC. So, as you can see over here, the coefficient of k core index is very small, 0.0007. So, even though it is significant, but it does not have much of a physical importance. Okay. So, it is like the effect size of the k core two members who are part of the same k core index are very less likely to debate. That is what I mean, like essentially it means, like they are likely, but not as high. The non-zero component, if you see minus 3.617, this minus signs means there is zero inflation, which means there are bunch of people who are not debating with each other. That is what it means. So, if this was like positive, it would have meant there is zero like the opposite way. Okay. The inflation is less. Sum over here, this sum 1.865. So, if you can take the calculator and do say exponential of 1.865. So, it means that ignoring all the attributes, the expected number of links between two parliamentarians is e to the power of 1.865. So, that comes around 6 point something the number. Okay. So, that is how you can kind of like interpret the coefficients. So, here I have given the value of BIC. This is not a standalone measure, you have to, it is basically used to compare. You have to compare the BICs being which one is the lowest. So, now let us say what if I add the gender term. So, interestingly you see the node match gender, which is the homophily term, is minus and there is a weak significance. Minus sign meaning that people of the same gender are less likely to debate. Okay, that's what it is meaning. However, what if I add the education part over here? So, I am not considering the gender part over here. Model 3 is the education part. So, here you see there is no education homophily, no effect is there, it is not significant. Okay. And in the final model, I add all the data, like all of them together. I see over here that there is a significant effect of the gender like only, although not much effect coming from the education. But from here, I have to choose the best model, that which one is best going to show the data, and that is based on the BIC score, it is model number 3, okay, minus 365076. So, that is the best model which shows that how the networks are getting formed. So, here let us take a look at 1960s, what happens next. So, here is 1960s. So, which one based on the BIC, which one would be the best model? First one, right, because it is the lowest BIC. So, interesting part over here in 1960s is that all these attributes actually does not have much of an like impact on your network. It is just through the graphs itself, the node properties of the networks itself actually predicts the whole network structure or the debate structure of your in this decade.
How do you simulate these numbers actually? So, what is the method?
So, it is not the algorithm is the method itself. So, it is like a logistic.
It's like a,
it's an
so it is like a, you find the
optimization, maximum likelihood.
yeah, you find the what is the most probable state
Yes,
in terms of physics.
yes, exactly. So, there is a theorem.
There is some constraint, and you find the most
yeah,
probable state.
yes.
So,
So, we have a theorem in 1971.
so these are constant, and why do you say there is this is based and this is not based?
Because of the
we just adding some constraint. So it's
I am not adding the constraints. I am adding the like independent variables. If I mean if you look it in that way, but just by adding, I cannot say the model is working good through the effect size or the significance, right? The best model will be shown through the BIC only, because that's the way it has to be done. So, the BIC here is the lowest in model 1. So, therefore, the network structure is getting predicted just through model 1, these variables in model 1.
My concern is that you can always find a most probable state irrespective of your number of parameters. You can always fit a model.
You can add like any number of like factors. So, that's, but this is I am using the one which I have in my domain at this point. So, you can add like say for example,
it can just reduce the number of microstate. So, if you add more,
as
in terms of statistical physics, if you add more number of parameters, so you are just adding more constraint, and that actually reduce the total number of microstate. So, you can get the most probable state there also, like
yeah, but if you keep on adding variables, you are adding like the VIF sort of a thing is going up, na? You cannot keep on adding just so. You have to make sure that the variance doesn't get inflated.
And but I'm here we don't have this goodness of the fit, like a BIC.
BIC is a very standard one. BIC is a very standard one. So, if you check the paper of 1995 by Raftery,
that is the social physics, but in the statistical physics,
physics, I don't care. I mean, this why should I care about statistical physics here? I mean, this is the.
No, but it's the same thing actually. So, it's the same partition function actually. So, that is my concern. So, there is nothing difference between the two.
No, I don't understand your point over here, because what I am trying to say is that which is the parameters which is best like describing the model, right? So, I can have all these attributes, but what I find over here is that, so the point is what you will see, like some people will just show you the model 4, because you have bunch of p values which are significant over here, but that's not the true picture, correct? The true picture is over here. So you can predict the whole network just based on this. That's the whole point. Okay. So then comes 70s. So just tell me which one you think is the best fit. 4, right? So interesting part, you find gender homophily in the data. Okay, although the sign is negative. So if you look into that picture, you see that in the highest K core index and all that, even though the gender had gone up a bit, in the highest core index, we had seen that the sign had fallen a bit, right? So like this, if you go along the path, let's say, so I don't see any node match with the highest degree, which is 0.008. I don't see any effects over here, but I see the effects of node match gender.
So what is the difference between the 4 models?
4 models is basically I am, so here the first model is like you can say a baseline model, okay, where I have chosen the network components, K core index, burst constraint and LCC. In this model 2, I am choosing the non-network components, which is the gender component. Model 3, I am focusing on the education part, right? And in model 4, I am taking all of them into like account.
Why is like the value of K core, say, burst constraint, why is it different than?
It has to be. It has to be because I am adding more parameters in the data. Right now in the burst constraint, so let's say if I had just taken the burst constraint on its own, the value would have been different. Okay, because I am taking it with 5 parameters over here, I am taking I think 1, 2, 3, 4, 5, 6, 7. So the values will be different. But the main part is that the sign of the burst constraint is not changing, and the value is going from 0.6 to 0.7, then to 0.5. So the change is not much. It's not like it is going to 0.05. Fine. So that's the thing. So values will be different because the coefficients will change. The more variables you add, the coefficients themselves will keep on changing. So let's take a look at the 80s now. So which one do you think will be the best over here? Huh? Model 3, right? So model 3 is the best model. Now what do you see different compared to the previous decade? What do you think is different over here now? It's the node match. The highest degree you see 0.024 and triple star. So what it means is that people with the same qualifications are more likely to debate in the 80s, okay, or they are more likely to debate. Then 90s, it's model 4, but here there is a factor of gender which is significant, but overall the node match, which is the homophily, is not. However, the interesting part over this in the 90s is that in 80s, although the node match coefficient was positive, in the 90s the node match coefficient of the highest degree is negative, which means what? If people, the parliamentarians of same education, they are less likely to debate in this decade. So in 80s they were more, in 90s they were less. So coming to the 2000 decade, here also I see the same pattern. So 90s and 2000 I see the same pattern in the whole description of the data, the significance of the data, and the decade which people would be more interested in, which is the last decade, will be what you see over here is the model 3. So, here also we see that people with same education in the last 2 decades, what we have seen in 2000, we see that there is like with the same education level, they are less likely to debate. In 2010 and 2021, I see the same picture, that if you are in the highest degree of the same order, same kind, you are less likely to debate. So, over the picture, what do we learn from here? So, this study, this temporal study of the networks, it gives me basically some mixed insights. There is no particular insight like a fixed insight as such that we have got, but one of the things is that how does it like impacts the policies of the government, which you can see. So, one is that the visual inspection, it provides insights into like highly clustered groups of individuals who are connected to members that rarely participate in the debate. There is a higher number of structural holes through the decades, and that reveals how the Rajya Sabha actually functions. So, members are not constrained by whom with the debate, rather they debate debating outside the cohesive pool of parliamentarians. The density, as I said, over time increased in the recent trend, which is basically showing like exit of veterans and entry of like new politicians in the parliament. Even though the representation of women in the Rajya Sabha is quite low, post 1970s, their presence in the core of the debate networks is quite high. The estimates of the valued Argam, they confirm that education and gender matter in the tie formation, but the intensity of the education homophily and gender homophily, they keep changing through the decades. And the interesting part over here is that the education homophily has higher statistical power than the gender homophily in the tie formation. So, I already talked about this based on the flip of the sign of the education homophily. Now, what can you do with this study? What more can be done? So, one of the thing is that the prospects, which is basically like to get the text of the debates. So, currently there are like I think like 11 lakhs such files which are there all total, close to I think 11 lakh I think. Which will be in the which is there in the PDF format. So, there what Shita Broda was like asking at that time, that you can have the sequence of the Q&A. Somebody asked, somebody answered, somebody asked, somebody answered. So, you can have a directed network as such compared to what I have done with the undirected one. And then like one of the things which I am right now trying to do is to get the state level factors, like which say constituency the parliamentarians are like say like standing for, their economic status as such. So, because these are some of the comments which came through the first time I tried to submit it in a journal. So, that is one thing which I am trying to focus on. So, if you have any questions, you can ask me right now, but like before I end, I just wanted to have a like I added this slide today based on the students. So, this is what a composition actually looks like. So, composition distribution which I talked about, which was my the reference distribution, is basically of this form. Okay. This is the Z and this is the probability. If this nu is equal to 1, then it goes to the Poisson. If the nu is equal to 0 and lambda is less than 1, then it becomes the geometric. So, that is what the Conwell-Maxwell Poisson distribution is all about. Yeah, so I end my talk over here. If you have any questions, I am free to answer, or any other comments.